Okay, let's talk about linear models and using a line to make predictions. In statistics, a model is a mathematical description, usually in the form of an equation, that represents something in the real world. In your introductory stats course, models are often used to describe the relationship between two variables. The idea is that if the relationship between two variables can be described mathematically, you can then use that description to predict the value of one of the variables, usually the dependent variable, based on the value of the other variable, the independent variable. So for example, we have a data set here of 9 observations. And what is the X and Y variable here? Well, it looks like the data observations come from birds, and X is the average weight in grams of the bird, and Y is equal to the average wingspan in centimeters for the 9 types of birds. So I've got the data entered into my calculator's list environment over here. And if I want to take a look at the scatter plot on the graph of the calculator, it's easy to do that. I'm just going to press second Y equals, and it looks like I've got my plots 1 and 2 on. So I'm just going to begin by turning both of my plots off, or all my plots off. So I'm pressing 4, hit enter. That's done. So when I press second Y equals, you can see all 3 plots look like they're off. So I'm going to select plot 1 by hitting enter, turn that on, and then select the scatter plot icon there. I need to tell the calculator where my data is at. I'm in list 1 and list 2. So this L6 needs to be changed to L2. So that's why I'm going to press second 2, because the 2 button becomes an L2 button when you press the second button prior to hitting the 2 button. So then I'm just going to press graph, zoom 9, and you can see, well, I've got my calculator drawing a line through that. I didn't mean to have that happen. And that's okay. I'll do that later, but there's what the scatter plot looks like. So you can see that it looks like there's a positive linear trend, or a strong positive linear correlation between X and Y. And so it might be good to use, and it looks like it's a linear relationship, so it might be good to use a linear model to describe the data set, or describe the relationship between the two variables. So we've got that scatter plot. It looks like this, it looks like that. Okay, it looks like there's a relationship, and it's a positive linear relationship. And of course, because the scatter plot is linear, you can use a straight line to describe the way in which the average wingspan tends to vary with average weight. The line Y equals 18.4 plus 0.15x has been added to the scatter plot on the next page here. I'm going to show you. And you can see it does a reasonable job of describing the pattern in the scatter plot. So this is what, and so this equation is a model for the relationship between average weight and average wingspan. Because the model for this relationship is a line, it's called a linear model. Whenever you have bivariate data, a model is an equation that represents the relationship between two variables. And if the equation used to model the relationship is an equation of a line, the model is called a linear model. If a linear model does a reasonable job of describing the relationship between the dependent variable y and the independent variable x, you can use the model to predict values of y, or values of the dependent variable. So for example, you could use the model y equals 18.4 plus 0.15x to predict average wingspan y, if you know average weight x. Suppose that the 9 types of birds whose information was used to construct the scatter plot of wingspan versus weight are typical of other birds with average weights less than 500 grams. Magpies are a type of bird that have an average weight of 250 grams. And the model equation can be used to predict the average wingspan of magpies by using the equation of the line to find the average wingspan that corresponds to an average weight of 250 grams. So the way that's done is, well, we just do a plug-in, right? We plug in the weight for X, and then we multiply and then add, and we're getting the model predicting 55.9 centimeters for the wingspan. So whenever we're going to find linear models called the regression line model for sample bivariate data. And we're going to use those models to make predictions and we're only going to do this when the relationship between X and Y is a strong linear relationship or correlation. Whenever you use linear models to make prediction, there is one thing that you need to consider. You should be cautious about making predictions for values of X that are outside of the range of the X values of the data set. This is called extrapolating. Do not extrapolate. For example, the 9 types of birds used to construct this scatter plot of average wingspan versus average weight all had average weights that were between 6 grams and 460 grams. There is no evidence that the linear pattern you see in the scatter plot would continue outside the range of weights from 60 grams to 460 grams. So it would not be, oops, let me get in there. So it would not be appropriate to use the linear model to predict the average wingspan of buzzards, because buzzards have an average weight of 1,300 grams, which is far above the range of average weights in the data set. So let's go ahead and measure the correlation for this data set. And we'll just use the calculator to do that. So the correlation number, remember, it measures the strength and direction of the linear relationship between X and Y. And we're expecting a strong positive linear relationship. And so we're expecting a value of R that would be significantly close to 1 or 100%. If you take a look at the formula, let me pull that up. The formula for R, Pearson's correlation coefficient, it looks like this. It's a clever formula that uses z-scores, and it's just the sum of the products of zx times zy divided by n minus 1, and here n represents the number of observations, so the number of ordered pairs in your data set. And the numerator, that's what it looks troublesome. But remember, we're just getting this value out of the calculator. And after I do that, I'll go ahead and show you how to use this formula by hand. And then let's talk about, after that, let's talk about the formula, why it produces the values it produces. Okay. To use the calculator, we've got to follow this list of steps. Here's that list of steps we're going to use to find the correlation coefficient R. So once you've got the data in list 1 and list 2, we want to use the calculator's Linreg TT test, or I'm sorry, Linreg T test So to get that done, we're going to follow this list of steps. Basically, I'm pressing the stat button over here after I've entered my data in. And then I'm going to right arrow over to the test drop-down menu. And I'm looking for the linreg t-test command. I don't see it, but if I scroll down, it's down there on the list of commands. Whoops, did I pass? There it is. Okay, notice there's a linreg t-test and a linreg t-int. We need the linreg t-test command, so I'm going to select that or highlight that and hit enter to select it. Okay, so now I'm getting this settings window, and it's similar to this settings window that you're seeing right over here in the diagram or the figure on the left. And we want to make sure that we're pointing, that our X list and our Y list are pointing to where we've located the data in the calculator. In this case, it's list 1 and list 2. Always keep your frequency number 1. And this B and P, don't even worry about that. Just make sure to set it to not equals 0. And you can find the best fitting line or the regression equation, the model equation. Well, we've been given that in this example, but you can also find that with this linreg t-test, and you can have the calculator store that regression equation as a particular function called y1. And then when we graph the scatter plot, it'll also graph the regression line or the model equation on our scatter plot. So right here where it says reg equation, I just want to tell the calculator to store that equation. And I just have to name that equation. And so I'm going to name it y1. And to get that done, I'm going to press the vars button over here. And then I'm arrow over to the yvars drop-down menu. When I hit enter, I'm selecting the function variables. And there's y1, so I'm going to hit enter. And then the calculator pastes y1 in right there. Let's go ahead and calculate. And we're going to get a printout which is similar to this. And a lot of this stuff I don't expect you to know, but the regression line equation is y equals a plus bx. And they do give us a value for a, the y-intercept, which is about 18.4. And they also give us a value for b, which is about 0.16. Okay, if you scroll down, you're getting some other things here. We'll talk about what those things are later, but you can see at the very end of your list, hey, I'm getting a value for r. And so that we know for this data value, this data set, we know that the formula here is outputting about 97%. So about 96.9%, or about 97%. So that is a strong positive correlation between X and Y. Now, if you had to use the formula by hand, that it wouldn't be that difficult, but it's not anything I would want to do. But just so you understand the formula, I'll try to go over that briefly. Okay, so the denominator of this formula is probably the easiest part to write out. And that's going to be the number of paired observations minus 1. If you go back and look, we've got 9 observations. And so the denominator for the value of r should be 8. And if we want to get this number for our numerator, that's where the trouble sort of begins. And so that's just why I recommend using the calculator the way I did to find r. But just so you know, I'll just do a little bit of this briefly, okay? So what we need to find to get this numerator is we need to find the value of zx and zy for each one of the values of x and y. So in other words, we're finding the z-scores for both the x and the y data. Zx will be x minus x bar over s since this is a sample of birds. And this is the formula for zy, that's going to be y minus y bar, so with y bar being the average, over s. And just so we don't confuse the two values of standard deviation, we're going to list this as sx and sy. Okay, so now to get that done, we might want to use a table. Grab another sheet of paper here. All right, so I think before I do find the z-scores here, I think it's probably a good idea to find values for x bar, y bar, sample sx and sy. Okay, so to get that done, x bar is the mean of the x data, which in this case, remember, is the average weights. So we are trying to find the average of the average weights. That's what x bar is. And then the standard deviation of those weights will be the number sx. The easy way to get that is to use the one bar stats command on the calculator on list 1 here. And so I'm getting that x bar, let me use a different color, that might help. Looks like x bar here is about 181. And the standard deviation for the sample of x values sx, that is roughly 158.9. Okay, so that means that the z-score formula for zx just simplifies to zx equals x minus 181.5 divided by 158.9. And if I do the same thing for the y values, I can simplify the formula for zy, and then it's easier for me to go use the formula. So that means I need to rerun the one bar stats command, but this time on the L2 list or the Y list. And it looks like I'm getting y bar, the average of the y data, is 47.7. I'm just going to round that, 47.7, rounding to the tenths. And the value of sy, the standard deviation of the y values from the sample, is about 26.4. Okay, so that means zy, that formula is just going to simplify to y minus 47.7 divided by 26.4. Okay, good. Now that we've got those two values, it's time to turn back over to our list of data and find the z-scores for both lists. Okay. Okay, so it might help to use a table to do this problem. So if you look at the data set, observation 1, that pair was 460 grams and 93. So that was the data from a barn owl. And to find the zx and zy for that point, we've got to use these two formulas here. right? We're going to put this value in for x here, and this value 93 in for y here to get the z-scores for these two observations. Okay, so to get that done, we're just going to, I guess I'll come down here. So zx, that's just going to be 460 minus 181.5 divided by 158.9. Okay, so we'll do the math on that to get the z-score of 460. And you can see it's about 175, 1.75 rather. So back to my table, that means this number is 1.75, the z-score. 460 is 1.75 standard deviation lengths away from the average of 181.5. All right, so the zy, we're going to plug 93 in here. And we're getting about 1.72. I'm rounding to the hundreds. So that means that this number in our table is 1.72. Okay, so if we're going to do, if you can remember what the problem is, I'm just showing you how to do this, how to calculate the value of R by hand. We already know that it's 97%. But just so you understand the formula, what I need to do if I'm going to continue to find this numerator of the formula, I need to find the zx and the zy for every one of the 9 observations using, using the formulas for zx and zy. Okay, so observation 2, if I want to find the z-scores, and this is the last pair that I'll do it for by hand, and then I'll also illustrate the formula just for the sake of time. Okay, so 370 has to go in for x. And we're getting about 1.19 standard deviations. And so that means this is 1.19 for zx here. And then finally the zy for this observation, we just have to put 70 in for y into this formula here. We're getting about 0.84 standard deviation lengths. Okay, fine. So you're starting to see how we're going to get this numerator. You first have to find the z-scores for all of the x values and all of the y values. So that's this list I'm making here. Okay, and I'm not, for the sake of time, and I don't want to bore students here, is I would have to do this 14 more times. There's 7 more observations in the data set. And so that would give me about 14 more calculations to put here and here. Okay, and for the sake of time, I'm not going to do that, but just so you can see how the formula works, then once you get these 2 columns filled out, the next thing to do is to multiply each pair of z-scores. So I'm going to take the numbers in these rows and multiply straight across these rows. Okay, so the first product would be 1.75 times 1.72. And the next product would be 1.19 times 0.84. Okay, so I'm finding all of the products, all 9 products of zx, zy. And then once I've got those products, going back to this formula here, okay, the numerator in this formula just says I need to sum up all of the numbers in this column here. So whenever you sum up these numbers, you'll get the numerator. Okay, and that's how the formula works. And so if I want to get this specific number in here, boy, I'd have to do all that work. I guess I could illustrate that work on the calculator just briefly. So if I want to get these 2 columns, zx and zy, on the calculator, here's how I would do it. Open up the calculator. So oops, let me start by rerunning the one-var stats command on x. Okay, so the calculator has now stored all of these values, and I'm going to call on those. So open up the calculator's list environment, and now I'm going to move my cursor to where it's highlighting L3, and I want the numbers in L3 to be all of these numbers, the z-scores for all of the x values. So I'm going to have the calculator plug this formula in for me, or I'm going to program that in. The way to do that is highlight L3, okay, and the x values are located in list 1. So right now I'm going to put second 1. Okay, now I've already messed up. What I needed to do was put a parentheses there. Now I'm going to press second 1. So I'm starting the numerator here, x minus x bar. So I'm going to call on x bar. And the way to do that is you can either plug in the 181.5, but that may not give you, but I'm not going to do that because it doesn't give you the precise value for x bar that was stored in the calculator. If I want to recall that value, then I'm going to press the vars button. 5 for the statistics variables. And you can see, you can call on all these list of variables. X bar is number 2, and I press 2 here. Notice how it pastes X bar in right here. I'm going to close parentheses. So that gives me my numerator, X minus X bar. And now I'm going to divide that by SX, which is going to be the stored value of SX in the calculator. So to grab that variable, I'm going to press the vars button. 5 for all the stored values of the statistics variables. And I'm going to want to put SX here. And then when I hit enter, bam, I'm getting all of these numbers in this list, all of the z-scores. And it doesn't round any of the numbers. So next thing I was going to do is get this list of numbers in the L4. So to get that done, I'm going to clear everything out of L4. And before I fill those numbers up, I need to recalculate the one variable statistics for the Y data. So I'm over here doing that. Make sure my list is L2. Okay, and now the calculator stores all these values for X bar, SX, and whatnot. So back over here to the calculator's list environment. I want to highlight L4, and I want to put in or program in this formula right here. Okay, so I'm going to call, let's see, the values of y are in list 2. So to write this numerator in the calculator, highlight L4, parentheses, list 2. That's where the y values are. And then minus, we need to go minus y bar here. But I'm actually going to call on x bar because the calculator has stored y bar as x bar. So I'm going to press the bars button, 5 for the statistics variables, and 2, and that'll paste in the value of y bar right there. I'm going to close parentheses and divide by sy, or the calculator has sx stored as sy. So call on the bars button, whoops, 5 for the statistics variables, and paste in sx there. And then when I hit enter, you can see I'm getting this entire column of z-scores for the y data in my calculator's L4. Okay, so if I want to get this product, then I'm going to go over here to L5, and I'm going to tell the calculator that L5 is equal to L3 times L4. So I'm pressing second 3 and see what happens. I put the L3 up and then times the second 4. So you can see L5 is going to be the products. When I hit enter, there's those products. If I want to sum up all of those products, there's a couple of ways to do it. There's a sum command, I believe. But how I'm going to do it is I'm just going to call on the one variable stats. And I'm going to do it on list 5. And once I do that, this number right here, summation x, that should be the sum of all the numbers in this column. So that tells me that this numerator is about 7.75, 456, and some change. So, and we'll see if this hand calculation now of R is close to this value. So hopefully it will be. Denominator is 8. And you can see bada bing, bada boom, bada bam, we're getting that value of R. So that is the hard way to find R. If you had to do it by hand, there'd be a lot more work, right? Never do the problem that way. Always find R, I would say, the way I showed you using the Lindbergh t-test. Okay, so yeah, we saw that the calculator came out with the value when we did the division. So now I want to go back to this. Remember, we were given the model equation, right? We were given the equation of the regression line here. And if you need the equation, if you need the equation for the regression line, you can get that by doing the Lindbergh t-test. I think I pointed that out earlier. So just don't forget about that. So it gives you the values for A and B. And you can see that those are the values right here. Oh, this one's slightly off, but that's okay. Okay, so that is correlation. Before I finish this topic of correlation, I want to go back over here to the book and take a look at the explanation they give us about the formula for correlation coefficient. And where is it? It's over here on page 170. I'm using the first edition of Roxy Beck here. And I want to draw your attention to these diagrams here. And keep in mind the formula. Let me write that formula over here. Okay, so we know these things right here. The correlation coefficient measures the strength of the linear relationship by using z-scores in a clever way. We know that this is the formula for the z-score of all the x values. And we know that x values in the sample that are larger than x bar will have positive z-scores, and that's always because your sample standard deviation is positive. And but more importantly, your numerator will be positive as well, because x will be larger than x bar. X minus x bar will be a positive number larger than 0. So x values that are larger than x bar will have positive z-scores, and if you have x values smaller than x, they'll have negative z-scores, because this numerator in this formula will be negative. The denominator is positive. You're going to divide a negative by a positive, so you're going to get a negative. The same thing can be said for y values and their z-scores. Y values larger than y bar will have positive z-scores, and those smaller will have negative z-scores. So keep this in mind when we inspect this plot down here. Here we are along the x and y axis, and for simplicity's sake, they put all of the points in the scatter plot in quadrant 1 of the coordinate plane. However, the argument that's made here can be made for points in any plane, any quadrant on the plane here. Alrighty. They've also got in the diagram a vertical line. It's through x bar and a horizontal line through y bar. So yes, the origin is right here. 0, 0 is right there. This diagram is a first quadrant graph of the coordinate plane for x and y. Okay, and they also put in, right, these dotted lines, the vertical and horizontal line that locates along the x-axis and the y-axis the values of the averages of the x and y data. And so then, if you take a look at points over here in this first region, okay, all of these points have a value of x, which is to the left of this value, which means they're larger than x bar. And so therefore the z-score for zx for all of these points will be positive. And now think about the y coordinates of each one of these points. Those y coordinates are all up here at numbers larger than the average. And so that means that zy is going to be positive. So then when you go to multiply these two numbers, zx and zy, for any points in this first. So what they did was, yeah, this is a first quadrant graph, but once you locate the mean, then you're dividing that graph up into 4 quadrants, okay? This is not the same 4 quadrants as the quadrants of the coordinate plane, but the quadrant 1, which is above y bar and to the right of x bar, all of these points will have positive z-scores, and so the product will be positive. And also take a look at values over here in this quadrant 3. All of these points, if you think about their x coordinates, they're going to be left of x bar on the x-axis, so they're less than x bar. So we expect the z-scores for those x values to be negative. Furthermore, all of the y values of each one of these points are less than the average y, and so that means zy will be negative. So then when you go to multiply zx times zy, when you're finding r, for all these points here, you're going to get a positive value for zx, zy every single time. Okay, so this plot is a scatter plot of points that indicate a strong positive relationship. And you can see what happens here. We would expect the value of r to be positive, and that's because most of these points here are located in these quadrants 1 and 3 as separated by the X bar and the Y bar. And if you take a look at the other two quadrants, well, you're going to find out the ZX is negative, ZY is positive, and so when you multiply those, you're going to get a negative value for that product. And the same thing can be said for points in region 4. Since there's not going to be a lot of points in region 4 for the case where we have a strong positive linear relationship, then these products ZX and ZY are going to be a relatively large positive number. So you can use the similar reasoning on this figure B over here, which exhibits a strong negative linear relationship, and it implies that this sum in the numerator will be a relatively large negative number. And that's because all of the z-scores for all these points will be negative. And all of the z-scores for these points will be negative. And yeah, you may have a point here and there, and they're going to be positive. But when you add up all of your, products, ZX, ZY, they're primarily going to add up to a large negative number. If you take a look at figure C below here, then you can see the correlation looks like it's pretty close to 0. It's not very strong. It doesn't look like it's positive or negative. And what's happening there is the positive and negative products that come out of the points from each of these, whoops, down here, these 4 quadrants, they tend to counteract one another, which will produce a value of this numerator, a value of the numerator here, which is not very big, so it's close to 0. So this number in the numerator of the correlation formula, it can be a really large positive number, larger than 7.75. It can be a really large negative number, or a number close to 0, depending on whether there is a strong positive, strong negative, or no strong linear relationship whatsoever. And it turns out that whenever you divide this sum by n minus 1, we did some math earlier, and we showed that that always results in a number between and including -1 and 1. Okay, so, and this is another reason why we can use the correlation number, or think of the correlation number as a percentage. It measures the percentage strength, and of course the direction is given by this sign, whether it's positive or negative. Okay, so just a quick word about correlation and causation now. A value close to 1 indicates that larger values of one variable tend to be associated with larger values of the other variable. This does not mean that a large value of one variable causes the value of the other variable to be large. Correlation will measure the extent of the linear relationship between x and y, but even if there's a strong relationship, the association or the relationship does not imply causation. It doesn't mean that x causes y. So it frequently happens that two variables are highly correlated, not because a change in one causes a change in the other, but because they are both strongly related to a third variable. Okay, so for example, among all elementary school children, the relationship between the number of cavities in the child's teeth and the size of his or her vocabulary is strong and positive. But the number of cavities in the child's teeth doesn't cause the vocabulary to be, larger or smaller. And no one advocates eating foods that result in more cavities just to increase vocabulary size. Number of cavities and vocabulary size are both strongly related to a third variable, age, so other children tend to have higher values of both variables, and that's probably the source of the correlation. And they give us another example here. Let's skip on down. Scientific experiments, okay, they can frequently make a strong case for causality, but you have to have careful control of the values of all variables that are related under the study. If you notice that y is observed to change in a smooth way, as the experimenter changes the value of x or controls the value of x, there may be a causal relationship between x and y. But in the absence of such control and ability to manipulate values of one variable, there's always a possibility there's an unidentified third variable that's influencing both variables under investigation. A high correlation in many uncontrolled studies carried out in different settings can also marshal support for causality, as in the case of cigarette smoking and cancer, but proving causality is an elusive task. So I guess the bottom line here is what she's saying here. Correlation does not imply causality, okay?